You can think of machine learning models as this incredibly powerful toolkit. But just having the tools, that's only half the battle. Knowing exactly which tool to grab, how to dial in the settings for the specific job you're doing, now that's what separates a decent result from a truly great one. So today, we're going to pop open that toolkit and take a good look inside. And really, that brings us right to the heart of it all. What is it that actually separates a good prediction from a bad one? And I'll give you a hint. It's not always about chasing the highest accuracy score. Nope. It's about understanding the trade-offs. It's about picking the right settings for the right reasons, and it's about measuring success in a way that actually matters in the real world. So, here's the game plan. First, we'll peek inside the machine's mind. Get a feel for the building blocks. Then, we'll get into the art of tuning these models. After that, we'll tackle the big question. How do you even know if your model's any good? And finally, we'll pull it all together and watch it play out by solving a classic data scientist's dilemma. All right, let's get into it. Before we can build amazing models, we've got to understand what makes them tick. Think of these next few things as the fundamental knobs and dials we have at our disposal to control exactly how a model learns from the data we give it. First up to bat is something called maximum tree depth. The best way to think about this is like you're playing a game of 20 questions. This parameter is basically you telling the model, okay, you can ask questions to figure this out, but you only get, say, 10 questions max. It's a simple rule, right? But its effect on how well the model performs is absolutely massive. And this slide right here, this shows you the tightrope we have to walk. If the tree is too shallow, not enough questions, it's just too simple. It completely misses the complex patterns in the data. We call that underfitting. But if you let it get way too deep, it starts to memorize every single tiny detail of the training data, including all the random noise. Then, the second it sees new data, it totally freaks out. That's overfitting. The goal is to find that perfect sweet spot right in the middle. Okay, so moving on to an even more powerful model, the random forest. One of the key settings here is, you guessed it, the number of trees. Let me ask you this. Would you rather get advice from one single expert or from a whole committee of 100 different experts? Yeah, the committee's decision is going to be way more reliable, right? It's the exact same idea here. Each tree is like an expert, and by averaging out all their opinions, you get a much more stable and accurate prediction. So, what about the heavy hitters, the neural networks? Well, their secret sauce is something called an activation function. Without it, a neuron is basically just a simple on-off switch, super limited. But with an activation function, it's more like a dimmer switch. It can have a whole range of outputs, introducing nuance and complexity. And that nonlinearity is what lets these networks learn the incredibly complex patterns we see in the real world. So, we've got the basic building blocks down. Now for the really fun part. How do we actually adjust all those knobs and dials to squeeze out every last drop of performance? This, my friends, is the art of model tuning. And one of the most important things to get straight is the difference between parameters and hyperparameters. It's actually pretty simple. Parameters are what the model learns by itself as it looks at the data. But hyperparameters, those are the rules we give the model before it even starts learning, like that maximum tree depth we talked about. Our job as data scientists is to find the best possible set of those hyperparameters. A perfect example of a hyperparameter is the learning rate. Okay, imagine you're in a super foggy valley and your goal is to find the lowest point. The learning rate is the size of the steps you take. If you take these huge, giant leaps, you might just jump right over the bottom and end up back on the other side. But if you get these teeny tiny little shuffles, sure, you'll get there, but it's going to take forever. Finding that just right step size is absolutely key to training your model efficiently. So, how do we test our settings without accidentally fooling ourselves into thinking our model is better than it is? Well, that's where cross-validation is a lifesaver. Instead of just one simple split of your data into a training set and a testing set, you chop it up into multiple pieces, or folds. Then you train and test over and over, each time using a different piece as the test set. It's a bit more work, but it gives you a much more honest and reliable idea of how your model will actually perform out in the wild. Okay, we've built a model, we've tuned it, we're feeling pretty good. But how do we actually know if it's any good? It turns out, good can mean totally different things depending on the problem. So how in the world do we choose the right yardstick to measure success? And here's the thing, just looking at one number can be so risky. For instance, say you build a model to detect a rare disease and it's 99% accurate. That sounds amazing, right? But hold on, what if the disease only affects 1% of the population? A totally useless model that just says no disease every single time would also be 99% accurate, but it wouldn't help a single person. See, you gotta look at the whole story. This little table here is basically your cheat sheet for understanding that whole story. Want a general report card on how well your model separates the good from the bad? Look at AUC. Is your dataset all lopsided, like our disease example? The F1 score gives you a much more balanced picture. But, and this is the important part, if one type of mistake is a total catastrophe while the other is just a minor inconvenience, then you have to zoom in on either precision or recall. All right, enough theory. Let's make this all real. Seeing how these concepts actually connect and work together in a real-world scenario is where the magic happens. So I want you to meet Priya. She's a data scientist, and she's facing a super common but super critical challenge. So Priya's job is to build a model that can predict whether a given system admin task is finished or not. Sounds pretty straightforward, but the stakes are really high. If her model gets it wrong, it could create a domino effect that causes massive delays for major projects. No pressure, right? And right out of the gate, she spots a huge problem. She looks at her data and sees that a whopping 80% of the tasks are labeled incomplete. This is a classic imbalanced data set. And why is that a problem? Well, because a lazy model could just predict no every single time, be right 80% of the time, and be completely and utterly useless to the business. This imbalance forces Priya to stop and ask what is probably the most important question in any machine learning project. Which kind of mistake is worse? Is it more damaging to predict a task is complete when it's actually not, what we call a false positive? Or is it worse to predict it's incomplete when it's already done, a false negative? The answer to this single question is going to define her entire strategy from here on out. So how does she crack this nut? Let's walk through the exact steps Priya can take, applying every single concept we've just talked about to build a solution that actually works and makes a real impact. And this right here is where the rubber meets the road. A false positive is a complete disaster. It means a vital task is forgotten, everything downstream grinds to a halt, and you end up with very unhappy clients. A false negative? It's just an annoyance. Someone wastes a little time following up on a completed task. It's inefficient, sure, but nothing catastrophic breaks. The path forward is crystal clear. She has to crush false positives. So, with that in mind, here's her plan. First, to tackle that data imbalance, she's going to use a clever technique called SMOTE to create more synthetic examples of completed tasks. Next, she'll pick a random forest model because they're great for this kind of problem. Now for the crucial part. Her primary metric will be precision because that's the one that punishes false positives. She'll also keep an eye on the F1 score just to stay balanced. Finally, she'll use cross-validation to meticulously tune her model to get the absolute best precision possible. And this is so important to remember. Her work is not done when the model is built, not even close. Getting it into the real world is a whole other beast. The model has to be properly integrated, the data pipeline needs to be automated, and this is maybe the most important part, she needs to build a feedback loop. She needs to let the actual system admins flag when the model gets it wrong. That feedback is absolute gold, because it's what she'll use to make the model even better over time. Which really brings this whole thing full circle, doesn't it? Building a genuinely useful predictive model isn't just a straight line from A to B. It's a continuous cycle. You have to understand the real-world problem, you have to carefully tune the technical bits, you have to evaluate it against what actually matters to the business, and you have to constantly keep your eye on the real-world impact. And that leaves us with one final thought. Priya's model is out there, it's live, it's working, but the world doesn't stand still. Data patterns change, business priorities shift. So the real long-term challenge isn't just building the model in the first place, it's keeping it relevant and effective over time. The model is deployed, now what?